So 2.4 covers infinite limits, and an infinite limit is a limit that equals infinity, or negative infinity. And usually we encounter infinite limits when we find vertical asymptotes on the graph. So vertical asymptote at x equals a, this happens. Sometimes the left-hand limit will be plus or minus infinity. The right-hand limit can be plus or minus infinity. Those are vertical asymptotes when that happens. If the left and right-hand limit happen to be the same infinity, then we can say the overall limit is plus or minus infinity. So we're just looking for where the limit, where the y value goes to positive or negative infinity. And one of the first ways we deal with this is graphically. We look at graphs and identify what's happening with these limits. So here's a graph that was copied from the book. This is h of x. And part A says, find the limit of h of x as h approaches negative 2 with a little negative superscript. So that's red. The limit of h of x as x approaches negative 2 from the left. So to figure out that limit, I draw a stick figure just a little bit to the left of x equals negative 2. And I look down to negative 2 to see where it looks like I'll end up. And you'll notice the graph goes all the way down here. At negative 2, there's a vertical asymptote, and the graph is going negative. So that's a negative infinity that the y value is approaching. So the left-hand limit is negative infinity. Part B is the limit as x approaches negative 2 with a positive superscript. That's the limit as x approaches negative 2 from the right of h of x. So to calculate this limit, I have to stand to the right of negative 2 and look and see where the graph is going. There's a vertical asymptote at negative 2, so I know the limit is plus or minus infinity. And since I'm looking down, that y value goes to negative infinity. So the limit as x approaches negative 2 from the right is negative infinity as well. Well, since the left-hand and right-hand limits are equal to each other, I don't need to put that superscript plus or minus on there. The overall limit is negative infinity, since it's the same from both sides. Now the other vertical asymptote in this graph happens at x equals 3. You can see the dotted line which represents the vertical asymptote. Well, part D asks me to find the limit of h of x as x approaches 3 from the left. So I have to stand on the graph to the left of 3 and look and see what happens to the y value there. And you'll notice that there the graph is going straight up, so the y value is going to positive infinity. So it's positive infinity as I approach 3 from the left. Part E, the limit of h of x as x approaches 3 from the right, the positive superscript. So to figure this out, I need to draw a stick figure to the right of 3, standing on the graph. And the stick figure looks over at x equals 3 and tries to figure out what the y value is doing. And if you look at the y value, it's going straight down, which means that the limit on the right-hand side is negative infinity. So I got a positive infinity for my left-hand side limit and a negative infinity for my right-hand side limit. And since those aren't the same, I can't have an overall limit. The overall limit doesn't exist because I have to know which side I'm on to tell if it's a positive or negative infinity. So that's how we do infinite limits graphically, just like we've done before, except now we're going to plus or minus infinity. If both the right and left-hand limits are the same, the overall limit exists. If the left and right-hand limits are different, then the overall limit doesn't exist. Well, you don't always have to do them with graphs. Sometimes you can evaluate them thinking about them analytically. So evaluating these limits analytically is you identify where the vertical asymptotes are. And you know at a vertical asymptote, the y value either goes to plus or minus infinity. So all you got to do is figure out whether it's positive or negative really close to that vertical asymptote. Because if it's positive when you're close to that vertical asymptote, then it has to continue going to positive infinity. If the y value is negative when you're close to that vertical asymptote, then it has to go down to negative infinity. So we test a value really close to the asymptote to determine which infinity it is. And here's an example. 1 over x minus 2. So this first problem is the limit as x approaches 2 from the left of 1 over x minus 2. And if we take 2 and plug it in for x, we get 1 over 2 minus 2, which is 0. That means there's a vertical asymptote at 2. So at x equals 2, it either goes to plus infinity or minus infinity. Those are the only options. Well, this says approach 2 from the left. If you're to the left of 2, you're a little bit smaller than 2. So what I want to do is plug in a number that's a little bit smaller than 2 and see if it's positive or negative. If it's positive, it has to continue up to positive infinity. If it's negative, it goes down to negative infinity when it hits the asymptote. So I'm going to choose a number very close to 2, but it's going to be smaller than 2 because I want to find the left-hand side limit. And numbers on the left-hand side are smaller. So I'm going to choose any number that's really close. How about 1.9? That's to the left of 2, and it's close. If I plug 1.9 in for x, I get 1 over negative 0.1, which is a negative 10. That is a negative number. I know that when x actually reaches 2, it's got to be negative or positive infinity. But when I'm really close to 2, it's a negative number. So that means the thing has to be going to negative infinity, because the y values are negative when I'm close to 2 on the left-hand side. So the left-hand limit is going to be negative infinity. I know it's going to be plus or minus infinity, and since the y values close to that are negative, it'll have to be the negative one. Well, for part B, we want the limit of 1 over x minus 2 as x approaches 2 from the right. Same idea. There's a vertical asymptote at x equals 2. So it's either plus or minus infinity. I'm going to test a number to the right of 2 that's really close to determine whether it's positive or negative. So maybe 2.1. So I plug 2.1 in there for x, and I get 1 over 0.1, which is a positive 10. So I know that when the number is to the right of 2, but really close, I get positive numbers. So that means from the right-hand side, it has to go to positive infinity. On the left-hand side, when I'm smaller than 2 and I plug in, I have negative values, so it has to be negative infinity. On the right-hand side, I plug in numbers larger than 2 that are close by, and I get positive numbers. That one has to go to positive infinity. But since these two limits are different numbers, the overall limit does not exist because it doesn't equal the two right and left-hand limits. So that's an example of how we can analyze a graph and think about what a vertical asymptote means to decide which infinity it is. We just pick a number really close on the left of 2, plug it in and see if it's positive or negative. Choose a number to the right of 2 that's really close, plug it in, see if it's positive or negative. And that'll help you solve the problem. So there's another example we have with trig functions. It's the cosecant of x. And it's a little weird to recognize that the cosecant even has a vertical asymptote. But I can rewrite the cosecant of x as 1 over the sine of x. So it's a little easier to see when you write it as 1 over sine of x that there's a vertical asymptote whenever the sine of x is 0. Well, when I plug in 0 for x, I get 1 over the sine of 0, which is 1 over 0. That's undefined because it'll make the bottom 0. So at x equals 0, the sine of 0 equals 0, and it gives me a vertical asymptote. So it's either plus or minus infinity. Well, to figure out which one it is, I choose a number. Now the first one, part A, is the limit as I approach x as x approaches 0 from the left. So I need to choose a number that's smaller than 0 that I can plug in and test. And I just have to look at what 1 over the sine of that number is. Now when you check this in your calculator, make sure your calculator is in radian mode. I guess you could do it in either mode, but it's safer to be in radian mode. So in radian mode, I'm going to choose a number that's a little bit smaller than 0. I'm going to choose x equals negative 0.1. And I'm going to plug it in. 1 over the sine of negative 0.1. Negative 0.1 is to the left of 0, but it's close. And when I plug this into my calculator, I get negative 10.0. That's a negative number. And I know there's a vertical asymptote here, so it's either going to be plus or minus infinity. Since the y values are negative when we're to the left of 0, this has to be negative infinity when I plug it in. The next one is the limit as x approaches 0 from the right. So I take 1 over sine of x, and I plug in a value for x that's slightly larger than 0, like 0.1. I plug that in to check out to see what kind of answer I get. And I get positive 10.1, or 10.0. I know there's a vertical asymptote at x equals 0, so it's either plus or minus infinity. Since the y values are positive here, this has to go to positive infinity on the right. Since the left and right hand limits are different, the overall limit does not exist because the one-sided limits don't equal each other. So there's another example of a function that has vertical asymptotes. Notice the trig can make it a little bit trickier to work through. Well, so the last example in this section has to do with finding all the vertical asymptotes. Now let me mention this fact. It's not really pressed in this section, but if I factor the top and the bottom, and I can cancel something out of the bottom, then the thing that I canceled gives me a whole, not a vertical asymptote. The vertical asymptotes are the factors in the denominator that are left over after you simplify. If it cancels in the denominator, it gives you what we call a whole, which is where you have an open spot in the graph. So to figure out the vertical asymptotes, I need to simplify f of x as much as possible. So on the top, I can factor that into x minus 7 times x minus 2. And the bottom, I can factor into x minus 3 times x minus 2. And when I do this, I can cancel the x minus 2 factor. So what that means is since x minus 2 canceled, then at x equals 2, there's a whole. Now what happens at a whole is you can evaluate it to find the limit there. It's not a vertical asymptote. You'll get a limit that's a number. So we don't care about that. What we care about are the vertical asymptotes. And the vertical asymptotes are the factors in the bottom that didn't cancel. So when I simplify this problem here, this becomes x minus 7 over x minus 3. That's the same function as the one we started with, except the one we start with has a whole at 2. But in this case, the vertical asymptotes, there's really only one of them. It happens where x minus 3 turns out to be 0, because we can't have a 0 in the bottom. The vertical asymptote happens at x equals 3, because that's the one that didn't cancel. Now if I want to figure out the limit of this vertical asymptote, I can do that as well. Now when I find the limit, I'm going to use the factored version of this function when I find the limit, because I know there's a vertical asymptote there, and at x equals 3, when I plug in 3 in the top and the bottom, that will be the same number in the top and the bottom. It'll just cancel. So if I want to find the left-hand limit, that's the limit as x approaches 3 from the left of x minus 7 over x minus 3. Vertical asymptote at 3. So I know it's going to be plus or minus infinity. Since I'm to the left, I'm going to plug in a number that's a little bit smaller than 3. How about 2.5? So 2.5 minus 7 divided by 2.5 minus 3, this gives me 9. That's a positive number, so I know at this vertical asymptote it has to approach positive infinity. We can also look at the right-hand limit. We can approach 3 from the right of the simplified version of the function. It's easier to work with. Since it's to the right, I have to choose a number that's bigger than 3 to plug in for x. How about 3.5? Oh, that's a minus 7 in there. I'm having trouble copying all of a sudden. So I plug in 3.5 in here for x. And when I plug that in, I get 3.5 minus 7 divided by 3.5 minus 3. And I get negative 7. There's a vertical asymptote at 3, and since the y values are negative, I know it has to be negative infinity that it's approaching. Since the left-hand and right-hand limit are different, the overall limit as x approaches 3 of x minus 7 over x minus 3 does not exist, because the right and the left-hand limits aren't the same.